All right, recording is on. It's March 12th, Math8680, and we are in the midst of combinatorial commutative algebra. Woohoo! So we've been talking about Kroll dimension and Noether normalization, systems of parameters, and maybe I'll remind you of what some of those many definitions were before we get back to regular sequences and Cohen-Macauliness and the magic of Cohen-Macauliness. It's a magical day. So let me remind you what was happening. It was back up in, it was way back there. I'll just say it again. Let's do this. We had recall that for R, a commutative graded K algebra, that the Kroll dimension was this number that we defined to be the maximum D, such that you can find D homogeneous algebraically independent elements inside R. So it is the max D, such that there exists theta 1 up to theta D that are homogeneous, they're elements of R, and algebraically independent. And it was, whoa, that looks like Imax, not max. It's not that exciting. Okay, but we had another way of saying it. It was the pole, the order of the pole at t equals 1 in the Hilbert series of R. And let's have in mind, just to remind ourselves of what some of these things were, another example that we didn't discuss last time. Let's take R to be a Stanley-Riesner ring for a simplicial complex that is an edge and a vertex. So I'll call that vertex A, that vertex B, and that vertex C, and also use them as variables in the Stanley-Riesner ring. So the Stanley-Riesner ring has variables corresponding to the vertices. And because who's not there is there's no edge from B to C, and there's also no edge from A to C, the minimal non-faces in this case are AC and BC. So that's the Stanley-Riesner ring. It's that quotient. And it has Kroll dimension 2. And for example, I can exhibit inside of it theta 1 and theta 2 being A and B are algebraically independent. Because A and B, they live on a simplex. And so you look at polynomials in A and B, they all survive in the Stanley-Riesner ring. And those polynomials in A and B, nobody's divisible by AC or BC. So they end up being algebraically independent, the A and the B. And so that gives you a lower bound of 2 on the Kroll dimension, but it turns out to be exactly equal to the upper bound. So in fact, we had this in general, right? If this thing is delta, then dim of the Stanley-Riesner ring we decided was equal to the dimension of delta plus 1. This is a one-dimensional simplicial complex because the largest dimension of a face in it is a one-dimensional face, but that means there are 2 variables that are algebraically independent that live on those kinds of faces. On the other hand, we could have computed the Kroll dimension by looking at the Hilbert series. Right, is the Hilbert series for this simplicial complex. And we know that's going to be H0 plus H1t plus H2 of t squared over 1 minus t quantity squared. And we could figure out what those H's are. Let's do it, because we'll keep working with this example. The F vector is 1, 3, 1, right? That's F negative 1, F0, F1. So I'm just counting empty face, vertices, and edges. There's only one edge. And then if we do the Stanley, the triangle trick to compute the H vector, let's see, this should be a 2. This is my F negative 1, my F0, my F1. 2 minus 1 gives me a 1 there, and 1 minus 2 gives me a negative 1 there. So H vector is 1, 1, negative 1. And so this is going to be 1 plus t minus t squared over 1 minus t squared. And the point is that this rational function, we knew it's going to be a rational function. For Stanley-Reisner rings, we even know that the denominator, that smallest denominator, is going to be that. And the order of the pole at t equals 1 is 2. Because that numerator, when you set t equals 1, you get 1 plus 1 minus 1. You'll get 1. And that's the F1, the number of d minus 1 dimensional faces. So you know exactly what the order of the pole is. Be okay?
So I know usually like H is all positive. So is the reason it isn't in this case because it's not a connected?
No, I disagree with you saying usually,
Okay.
Alex.
Well,
Right?
there's all these millions of theorems about it.
Right. Usually in this class, we're interested in these very well-behaved rings where the H is
Okay.
positive. Yeah.
Okay. I think
Right.
I've only seen examples of those, so it horrified me to see a negative H.
No. That's part of the point here is exactly what
Yeah.
are the good versus bad. And good in some sense is rare. It's just that, so many things we care about in combinatorics have the good property of Cohen-Macauliness, right? We're headed toward Cohen-Macauliness. And we
Okay.
saw
Yeah.
that shellability implies Cohen-Macauliness, shellability implies partitionability. Both partitionability and Cohen-Macauliness you should regard as, ooh, that's extra good behavior. So it's not usually, it's kind of nice and special. Yeah. Good.
Okay. And then, yeah, this is not a Cohen-Macaulay.
This is not a Cohen-Macauliness. Exactly. Yeah, we're headed there, that this is an example of a small non-Cohen-Macaulay complex. Exactly. And this was the clue. Yep. Good. All right. So then we had this concept of also recall that we said theta 1 up to theta d for d, the Kroll dimension, homogeneous, are called an HSOP, homogeneous system of parameters, if when you look at R mod theta, the quotient ring is actually now down to finite dimensional over the field, which means Krull dimension 0. Okay, so you mod out by them, and they're exactly the right number of them, and they have this property so that they cut it down to Krull dimension 0. You can check that, so some of the things you can show, it'll be a consequence of what I'm about to prove in a moment, that every time you mod out by a theta, you can at most drop the Krull dimension by 1. It might not go down at all, but at most it can drop by 1. So if you mod out by an HSOP, that means at every stage, if you thought about doing it sequentially, each further modding out by a theta I would have dropped the Krull dimension 1 more. Okay, so these were the important things so far that we've defined. And the one that we were talking about last time was regular sequence. So we said, and we said theta 1 up to theta k, say, are, and okay, and now this is again a pain in the butt, but I need to introduce modules over R because I need to talk about R mod theta 1 and R mod theta 1, theta 2, and so on, are a regular sequence on an R module M if theta is a non-zero divisor on M. Oops, yeah, is an NZD. It's weird. It's an NZD on M. Theta 2 is a non-zero divisor on M mod theta 1. Dot, dot, dot. Theta k is a non-zero divisor on M mod theta 1 plus theta 2, and so on. Theta k minus 1 M. So you keep modding out by them, and they remain non-zero divisors even after you've quotiented by the previous ones. That's what it means for them to be a regular sequence. And it sure looks like it depends upon the ordering. in which I wrote them down, which for arbitrary commutative rings would be true, but in this graded setting, that can't happen. So we had stated something that let me put it down here. Proposition. We said for m not equal to 0, theta is an R sequence if and only if, excuse me, is an M sequence, an M regular sequence. If and only if, yes. One way to say it is the relationship between the Hilbert series when you mod out by them and before you mod out by them is totally predicted by their degrees. Namely, it's 1 over 1 minus t to the degree of theta I, that product, excuse me. And this is going to force, actually, this thing is the Hilbert series for the subalgebra that they generate inside of R. So you get a product relation between the Hilbert series of the quotient, the subalgebra generated by the things you modded out by, and the original. That's the complete predictability I'm talking about. And that does not depend upon how I ordered the thetas, right? Because this expression certainly doesn't, and neither does this. All right, and another way we said this is it's if and only if M is a free k of theta 1 through theta k module. And the thetas are algebraically independent inside of the ring. So that their Hilbert series of their subalgebra that they generate does look like this. Okay. So again, this way of saying it has nothing to do with the ordering on the thetas. All right, so before I prove that, let me just point out a couple of things about this. In particular, let's just take the k equals 1 case for the moment. Theta 1, just being a non-zero divisor means the relation between the original Hilbert series and the quotient by theta 1 is just a 1 over 1 minus t to the degree of theta. Every time you do that, you multiply by this expression. What you're doing is, how do I want to say that? Let me rewrite it this way. The Hilbert series of m mod theta is this times this. That gets rid of one of the poles, t minus 1. It gets rid of 1 in the multiplicity, the order of the pole. So it drops the Kroll dimension by 1 when you mod out by a non-zero divisor. In particular, if theta is a non-zero divisor, is a can never figure out how to write that. A or n is a non-zero divisor on M, then excuse me, and I'm going to write this for R. This is a special case. Then the dimension of R mod theta, the Kroll dimension, is 1 less than the dimension of R. And if you have a regular sequence, you just iterate this. This is an R regular sequence. Then it drops the Kroll dimension by k. Each one of them drops it 1 more. Okay, and that's just seeing what happens with the order of the pole between these two. You just check that you've eliminated one from the order of the pole at t equals 1 in that case. All right. In particular, if you were able to come up with the Kroll dimension many, if you could get k equal to d as the Kroll dimension of R and find such a regular sequence, then you would have dropped it down to Kroll dimension 0, and the quotient would be the original thing would be a free module over the subalgebra that they generate, or this, you'd have this relationship between the Hilbert series, the quotient, and the original, and that's the Cohen-Macaulay case that we're heading toward. Okay, so I'm going to try to prove this, at least part of this proposition. Any questions about this? So let's leave the statement there for the moment and start proving it. So in fact, what it makes most sense to do is really work one at a time with each theta and see how does the relation between the Hilbert series of m mod theta and m, how do they relate in general, whether or not it's a non-zero divisor. So let's just write down the lemma that tells us exactly how to see how the Hilbert series changes when you mod out by a homogeneous element, theta. So I'm just going to write down, yeah, in fact, the first if and only if just entirely comes from the following lemma, just iterating it. All right, theta homogeneous in your graded ring R. It's going to have that the Hilbert series of M is less than or equal to something that looks really similar. The 1 minus t to the degree of theta times the Hilbert series of the quotient. Oh, I need the quotient, m mod theta m. And what's this less than or equal to mean, right? This thing's a power series in T. This is also a power series in T. This is also a power series in T, right? I mean, just to remind you, it's good to think about this. This power series in T is 1 plus t to the degree of theta plus t to the 2 degree of theta and so on. It's a geometric series. Right. So this less than or equal to that I'm talking about is going to be some less than or equal to in power series land, and it means coefficient wise. Coefficient wise less than or equal to in the power series. So what is this partial order that I'm talking about, this less than or equal to? If you want, I could make it a curly less than or equal to, but let me not do that. What I'm saying is you take, for example, this power series minus the one that you see on the right, it's got coefficients, they're all non-negative. That's all I'm saying. Take the difference between the left side and, sorry, the right side and the left side. This one minus this one is a power series with non-negative coefficients. That's like a partial order on power series. If you define your less than or equal to that way, you realize, oh, it's transitive, it's anti-symmetric, you know, so it's reasonable to call it less than or equal to, this coefficient-wise less than or equal to. Okay. And with equality, and that coefficient-wise is less than or equal to, if and only if theta is a non-zero divisor. So what am I saying? That you're going to have this equals this if and only if theta is a non-zero divisor on M. And now I claim if you iterate this, you know, for the theta 1 through theta k, you're going to get, in the non-zero divisor case, you're going to get equality here. You're just going to keep multiplying by these 1 over 1 minus t to the degree of theta i's. And in fact, if you ever didn't have a non-zero divisor, you're going to get a strict coefficient-wise inequality. In other words, you'll have less than or equal to on all the coefficients, but some of them will be strictly smaller. Okay? Everybody see how this lemma would prove the first if and only if? And in fact, what am I going to really do is I'm going to turn that less than or equal to into the thing that we really show. So proof. Let's prove an equality. Precise thing, which is Hilbert series of M of t. How does it relate to the quotient? Well, it's equal to the same expression in front. And then what you got is the quotient, its Hilbert series, minus something that's got non-negative coefficients, namely t to the degree of theta times the Hilbert series of the annihilator of theta on M. Remember the annihilator? That's the thing that checks whether theta is a non-zero divisor. Theta is a non-zero divisor if and only if the stuff in M, which is annihilated by theta, is just zero. Let me remind you, that thing is zero if and only if theta is a non-zero divisor. Okay, so let's think about it for a moment. If we can prove this, right, let me just call this precise equality statement. That proves this. Because Hilbert series of this minus the Hilbert series of this is this times this, something which is non-negative. Sorry, I got that wrong. This minus this is equal to this times this. That's non-negative, and it's zero if and only if theta was a non-zero divisor. Maybe that's a lot to process right now, but come back to these notes, you'll get it. Everybody okay with why star is really the key point for that first if and only if? Okay, star, the proof of star, is the most homological I'm ever going to get in this entire class. Like, I've already warned you that I've been doing short exact sequences, which are nothing. They're like just quotients. This is the quotient to that and that. I'm going to short exact sequences. They've got 3 terms. I'm about to use 4 terms. It's going to be a kernel co-kernel exact sequence, and that's it. We'll never get more homological than this. If you hate homological algebra, fine, close your ears. If you're okay with it, I promise this won't be too bad. Okay, so how do we do it? To prove this, let's just continue. You know I like long sentences. By constructing the kernel co-kernel sequence for this map. Okay, so what's a kernel co-kernel exact sequence? It's just when you got say a map between vector spaces or modules or whatever it is, some situation where you can talk about kernels and co-kernels, and you say, if I look at B mapping onto the image, that quotient map is of course surjective because, right, B onto a quotient, that's always surjective. So we have exactness here when I put a 0. And then, yeah, we just made this thing correctly constructed so that it's exact here. B mod the image of F is exactly that. So F of A is the kernel of this map. And then how do I make it exact at the next stage? I just put the kernel of F here. So whenever you have just a map between A and B, you always can write down this 4-term exact sequence of whatever. Vector spaces, modules, graded vector spaces, I don't care. And I'm going to consider it for the particular situation where I map from M to M and I multiply by theta. I'm just going to look at what theta does when it multiplies on M, right? We're worried about whether theta is a non-zero divisor. Does it have any annihilator? Now notice, that means that immediately the annihilator on M of theta is the right thing to put there for the kernel. That's the definition of the annihilator. It's this map is M goes to theta M. It multiplies by theta from the ring on the module. So the annihilator is its kernel. And notice, M mod theta M is the right thing to stick there because the image of that map is theta M. And the only thing that's wrong in this picture, so there's nothing wrong with it so far, except in order to make these maps graded, right? M was supposed to be a graded R module. This is a graded R module. If theta was homogeneous, it had a certain degree. The one thing that's wrong in this picture is that it looks like if M was in a certain degree, that this thing is in degree of theta plus M. This map's not homogeneous. So what do? I make it homogeneous. I do what the commutative algebraists always do. I do a shift of degree. Am I going to call it delta? No, let me call it this. Minus delta if degree of theta is delta. Now, what does that mean? So this is a commutative algebraist notation. I'm sorry about the minus sign. This is one of these things where the commutative algebraists apologize because the algebraic geometers made them do it. I'm doubly apologizing because I'm a combinatorialist, and I apologize for the commutative algebraists who have to apologize about the algebraic geometers. So this means the same module M, but everyone's degree is shifted upward by delta. And somehow the point is in algebraic geometry, this would have been like you tensored with some line bundle, where you shifted by a positive power of the line bundle rather than by a negative. This would be shifting by a negative power of the line bundle. Who cares? It's just their convention. So now that everybody's degree has been shifted up so that this thing lives in degree M plus delta, it's mapping to something of the same degree. The maps are all homogeneous. They preserve degrees. They map between the homogeneous components of the same degree. Okay, if that was really confusing, come talk to me in office hour. I'm still lonely there. Everybody okay? Good. Now what's the point? When you have an exact sequence of vector spaces exercise, and this is an exercise definitely I'm not going to put on your homework. This is just like homological algebra 101. If we've got graded vector spaces, modules, I don't care what they are, but they're graded and exact, then that implies that the Hilbert series, you take the alternating sum of their Hilbert series, and you will get 0 as power series. Okay, in other words, take the Hilbert series of this one with a plus, minus this one, plus that one, minus that one, plus that one. You alternate the signs, and you will get the 0 power series. And the reason is, since what you really have to do is just work degree by degree and say the same thing about vector spaces and their dimensions. If this is exact as vector spaces, then the same is true, that the dimensions go like that. The alternating sum of the dimensions in an exact sequence is 0. And so all you do, this is the exercise you should really do if you've never done it. This is homological algebra 101. We're only going to need it in the case of a 4-term thing, but may as well just prove it in general for vector spaces. And then here, because the maps are homogeneous, they're preserving degrees, you just work degree by degree, and you deduce this about these power series coefficient by coefficient. And Sasha asks, what is the map from the annihilator? Ah, thank you, Sasha. You're constantly saving me. Good. I'm assuming the reason you asked is because it wouldn't have been correct without doing this. It's the inclusion from the annihilator, also with its shift in degree, into M itself, shifted in degree, yes. Really, it's just the inclusion of the annihilator, but I do have to get the degree shift right. Thank you for asking. And that's going to come up in this, that's going to come up in this computation in a second. Okay. All right. Why should that help? you just take this exact sequence right here, and you apply that. And let me see what's the best way to write it is, okay. This gives, I'll write it like this. Yeah, let me start with the left end. T to the delta, shifting the Hilbert series of the annihilator. Can I leave out the T's in the Hilbert series? I'm leaving out the T's in my Hilbert series. There's a comma T in all of them. Minus, the next one is T to the delta times the Hilbert series of M. Plus, the next one is just Hilbert series of M without a shift. Minus, who's the last one, is the M mod theta. Equals 0, right? So what happened here? This T to the delta times the Hilbert series of M, that is the Hilbert series of this thing where I artificially moved everybody's degree up by delta. And this one is the Hilbert series for the annihilator, where I artificially moved everybody's degree up by delta. And notice the plus, minus equals 0 because of the exactness. Okay? And so, yeah, what does that give us? Let's put the Hilbs together, and we get Hilb M with a 1 minus T to the delta. That was combining these two terms is equal to, yeah, the other ones on the other side are going to have this with a plus, this with a minus, Hilb with a quotient, minus T to the delta times the Hilb of the annihilator. And that's it. That's what we said we were going to prove, right? You just have to bring this over there, divide by that. Let's check that that's right. Yep, that's star. Everybody okay? All right, not very homological, but it's just, you know, keeping track of what happens when you multiply by theta and what it does to Hilbert series having to do with the annihilator. Questions? Okay, I think for the, what was else? There was another if and only if in the proposition. We just did that so far. This one, I think this second one, I'm just gonna say, come to my office hour. I don't want to spend forever doing this kind of generating functionality, commutative algebra stuff. I feel like it's only so interesting. So let's leave off that second if and only if, and we'll say you can come to my office hour. It's not hard, but I only have so much stomach for this. Okay. Good. Can we define Cohen-Macaulay now? Yeah. Maybe depth too. All right, I did define Cohen-Macaulay for Stanley-Reisner rings before, but this is the more general definition. Say the graded commutative K-algebra R it's Cohen-Macaulay if there exists a homogeneous system of parameter theta 1 up to theta d, where d is the Krull dimension, which is also our regular sequence. In other words, theta 1's a non-zero divisor, mod out by it, and theta 2's a non-zero divisor, dot, 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 all the way down. Or the whole thing, R itself, is a free module over the polynomial subalgebra that the theta 1 through theta d's generate. It will force them to generate a polynomial subalgebra. They will force to be algebraically independent because they're a system of parameters. We already said that back with systems of parameters, that it forces them to be algebraically independent. Okay, and properly speaking, again, this is just for terminology's sake, for your culture, because I don't want people to sue me when I taught you a class and didn't tell you the word depth. In fact, we should really define, one can define depth of R to be the maximal length such that, well, let me call it maximum. I shouldn't call it D because that I was reserving for the call dimension. Maximum, I don't know, K, such that there exists an R regular sequence of length K. And so Cohen-Macaulay'ness is saying that the depth is as large as it could be, namely the Krull dimension. Depth of R equals Krull dimension of R, right? That's, again, that's Krull dimension. There's always an inequality, right, from what we've been saying. We're saying this is the case of equality. Why is there an inequality? Is because, right, we said that the depth, every time you mod out by one more element in a regular sequence, your Krull dimension goes down. It can't go below 0. And so that depth better be at most the Krull dimension of R. I've missed a couple questions in the chat. D for Krull, K for T. Yeah, it's horrible, isn't it? Why did Krull put his name on vector spaces, the fields too? I hate that. Yeah. All right, so. Okay, so we know what Cohen-Macaulay means. It means you've got a regular sequence that's as long as it could possibly be. But here's the weird thing. Note the quantification, the existence of a system of parameters, which is a regular sequence. Part of the magic of Cohen-Macaulay rings is the following assertion, maybe one of the most important things. This is a non-trivial, surprising, and incredibly useful fact. Surprising? No, surprising. Theorem takes work. When you have a Cohen-Macaulay ring, every homogeneous system of parameters will be a regular sequence. Once there's one of them, they all are. This should not have happened, and yet it does. This is, I don't know how many of you have ever heard Mel Hoxter's famous, something he wrote in a paper. It gets quoted a billion times when you start talking about Cohen-Macaulay rings. He wrote, life is really worth living in a Cohen-Macaulay ring. It horrifies me to think of like what it's like living in a non-Cohen-Macaulay ring, but anyway, I don't usually live in rings. But let me just say, I think of this as part of the magic of Cohen-Macaulayness. There's a lot of magical things. I'll tell you about another one later when we talk about Gorensteinness. And we're going to stop writing Cohen-Macaulay. By now we've written the word of a billion times, and we're just going to say CMness. The magic. It's like being at Disney World. Okay, time for some examples. Whoa, that was a lot of theorems, propositions, definitions. We ready for some examples on top of our definitions? Okay, so you've seen me define Cohen-Macauliness for Stanley reasoning rings in a different way, but it's consistent. It's just that now we know they have some more properties. Like if I took this delta, this is not the one I had before, A, B, but I am going to put an edge from B to C, this delta. And we look at its Stanley reasoning ring. Well, it looks a little different. It's got still the 3 variables, but now the only non-face, minimal non-face that I have to mod out by is there's no edge from A to C. And so slightly different quotient, different from the one before. This thing is Cohen-Macaulay. Since delta is shellable, right? I can order those facets, I don't know, F1, F2, boom, that's a shelling order on that little connected graph. I've ordered the facets in a shelling. So we know that if we take any linear system of parameters, right? And we know exactly how to test these, theta 1, theta 2, for example. I don't know, I'm going to write some down in terms of their coefficient matrix. What do I need to make happen? Well, here's something in your homework. I can't remember which homework problem this is. Maybe it's number 2. I say, try theta 1 is A plus B plus C is the sum of all the vertices. That one is always a non-zero divisor in any Stanley reasoning ring. That's what you're supposed to prove in, I think, problem 2A or something, or one of those problems. But then the theta 2, I don't know, let's take, this will work, I think. Let's take theta 2 just to be B. Let's just check our usual criterion. I look at each facet, I see A, B, and I look at the matrix. Yep, maximal rank. And I look at the other facet, F2, I look at the submatrix. Yep, maximal rank. Good. I don't have to worry, since AC was not an edge, I don't have to worry about the fact that this submatrix is actually singular. I don't care. That was not a face. So that's a system of parameters. And this thing is going to have, yeah, you know, K of delta, a free K of theta module. And we even know a basis from the shelling with basis coming from the, you know, we take these X to the GIs, the shelling gives a partitioning. We look at those minimal non-faces GI, and what do we get? Like F1 gives us the monomial 1, and F2 gives us the monomial A from the shelling. And, you know, it's, you know, as we saw, that this means that the Hilbert series of K of delta is going to be, yeah, 1 plus T, because this thing's of degree 0 and this thing's of degree 1, times the Hilbert series of that subalgebra that these things generate, right? This is, it's the Hilbert series of the subalgebra generated by theta 1 and theta 2 times the 1 plus T that come from the degrees of our basis elements. Sound right? This is this Kind-Kleinschmidt theorem. We proved it using shellability. But now let's see a little bit of the magic. I'm going to pick a different system of parameters. It doesn't have to be linear, but it should still work. That when I take that system of parameters, I should get that they are a regular sequence. Any BA so let me like take the, I don't know, same theta 1, A plus B plus C, but I'm going to do another theta 2 that I happen to know. Actually, one that always works is if you take theta 1 was the sum of the vertices, the vertex variables. Theta 2, take the sum of the edge monomials, so AB plus BC. And then theta 3 is the sum of the triangle monomials, the two simplices, and so on. That will always work, turns out. This, by the way, is closely related, if any of you know Ashley Adams, is closely related to what she and I were writing a paper about recently, is this particular choice of system of parameters. Notice it really is homogeneous, but not of degree 1, right? This is degree 1, degree 2. And let's just check, right? The Hilbert series. So I'm going to look at the, actually, let's just look at the quotient by these two. I want to convince you that this is a system of parameters. So we start with the 3 vertex variables. We had to mod out. I'm just going to remind you what the complex looked like. It looked like this. We had to mod out by AC. And now I'm modding out by A plus B plus C. And I'm also modding out by AB plus BC. And how am I going to think about this? Well, let me use this, right? Since I'm setting A plus B plus C as 0, you could think about that as B is getting set to negative A plus C. And just get rid of the B variable. I claim that this is isomorphic to, as rings, just having 2 variables, A and C. I still have to mod out by the AC. I no longer need this relation because the B variable is gone. And what is this one? This one is B times A plus C, and B is now negative A plus C. So this is minus A plus C squared, right? That's what happened there is I took that relation and I rewrote it since B is the negative of A plus C. Everybody okay with that? And if you think about it, this thing, if I rewrite it a little bit, what is this? This is A squared plus C squared plus 2AC with a minus sign in front. So I claim maybe we could think about this ring a little differently as the quotient ring is isomorphic to K adjoint AC, A and C as variables. We've modded out by the monomial, the quadratic monomial AC, and we've also, I don't really care about this one anymore because I've already modded out by the AC. I don't need that to generate this. So I've set also, and I don't care about the minus either. I claim this is the same as that quotient. In other words, these two things generate the same ideal as these two things. It's just I'm rewriting generators for the ideal. Sound okay so far? Stop me if I make a mistake. We know I do. And so I'm just going to write, this is the K span of some things in various degrees. In degree 0, the scalars, I still need the 1 to span it over the fields. I still need the 2 variables, A and C, in degree 1. So this was, degree 0 was here. This is degree 1. What about in degree 2? If I throw in the A squared, then I don't need the C squared because C squared is the negative of A squared. And I don't need the AC because that's 0. And actually, this is the end of the story. For example, C cubed is A squared times C is negative A squared times C because C squared is the negative of A squared. And then this is 0. So this is 0 because it's divisible by AC. That thing in the cubes, in the cubic part, is 0 in this quotient ring. I'll let you check. A cubed is also 0 in the quotient ring. A squared C is 0 in the quotient ring because AC is 0. And AC squared is also 0 in the quotient ring because AC is 0. I'm trying to convince you there is no cubic part, nor quartic, quintic, etc. This thing stops after degree 2. So these two in this particular example, they really were a system of parameters because we modded out by them. There were 2 of them. It matched the crawl dimension. We modded out by them and we got down to degree 0, crawl dimension 0, a finite dimensional K vector space. And let's just check that the Hilbert series is right. I wrote M, but I want to say Hilbert series of the quotient is 1 plus 2t plus t squared, right? Because what happened here, I've got, this was degree 0, this is degree 1, this is degree 2, 1-dimensional, 2-dimensional, 1-dimensional. So that's the Hilbert series for the quotient. 1, 2, 1 are the coefficients. And that is, correctly related to the Hilbert series for the original, right, was 1 plus t over 1 minus t squared. We did that using a different HSOP. But the point is, this is what we would have gotten if we had written it with the appropriate degrees here. So let me emphasize, these 2 are these 2. So the quotient there in the numerator and the thetas, one of them was of degree 1, one of them was degree 2. This is exactly right. Check me on this, right? One of these 1 minus t's, you can turn into 1 minus t squared if you put in an extra 1 plus t in the numerator, which multiplies out to that. That's part of the magic of Cohen-Macaulay's. Any system of parameters will give you the appropriate relation between the original ring and the quotient, or Hilbert series. Okay, we have gone way over there, but it was important to do an example of the magic. Any questions before I turn the recording off on the video?